Okay, so in this third part of the statics with wrenches series, which turned out to be much longer than I anticipated. I didn't think I was going to do a three-part series when I started this. We'll look at this cute dog here. So the idea is to look at this is basically a half-quadruped. So I'm interested in robots, and a quadruped is a robot with 4 legs. Like a dog, right? So we actually bought a small dog robot recently, an Uni3 A1. And part of the reason why I'm interested in all of this is because I'd like to play with the dog and understand its dynamics and statics, which I think is a prerequisite to understanding dynamics. So in this case, we have a planar version of this dog. We have 5 links. We have A, B, C, D, and E. So I called the body frame E. But we are not modeling the back legs. We're just modeling the front legs here, and think of this entire thing as in the plane. And that's often sort of a first step in analyzing robotic systems, because you get a lot of intuition, and thinking in 3D is much harder. But in fact, the recipe that I outlined in the first part of this series, which is this, I can show it again, okay? So, because it's in the same notebook, for each joint we define a parent and child link, then we define an unknown wrench for each joint, but expressed in its child link frame. And then we have one balance equation per link, okay? This exact same recipe can be applied in 3D as well. So there's nothing here that prevents you from modeling all 4 legs with almost the same code. Instead of pose 2, which is the SE2 class of GTSM, you would use a pose 3, right? But then you probably need 4 legs, in fact, to counter a torque and make the robot, otherwise the robot would fall over outside or inside the plane. Here we'll do that 2D example, okay? And following the recipe, we have 6 joints, all right? So we have 2 at the feet, 2 at the knees, and 2 at the hips. So this is a 2-link leg. And so we have, let me just move out of the way here. We have 1, 2, 3, 4, 5, 6 unknown wrenches. This is SE2, and SE2 wrenches are 3-dimensional, forces in X, in Y, and a torque. So these are 18 scalar unknowns, but we think of them as multivariate wrenches, which are row vectors, right? So, again, we can actually, analytically eliminate the wrenches and get some expression for the torques. And so what I'm going to do is I'm going to follow robotics tradition here. And but you don't have to do that, so you can do everything with GTSM, but just to make the link with traditional robotics lingo, I'm going to do that here. So I'm going to say, look, the torques are just the axes times, so the wrench times the axis, and we can do that for all 3 torques in a particular leg. So let's look at one of the legs, in this case the hind leg. But the same math goes for the front leg. And writing this here, T1, T2, or Tau1, 2, Tau2, and Tau3 directly as a function of the wrench in the in joint 3 here, is really analytically eliminating these 2 unknowns and then expressing the torque in these analytically eliminated expressions. So here we go straight from the wrench here to the torque here and to the torque here, and also to the local torque, which is Tau3. All right. Note that the wrench expressed here is expressed in the body frame, Okay, so we also need an axis even for torque 3. Yeah, and so let's consider this torque, these 3 torques as a vector, right? If you consider them to be a 3 vector, then we can sort of collect these 3 equations here and write this as the multiplication of a wrench, which is a row vector, with this Jacobian, which is going to be a 3 by 3 Jacobian. In this case, we have 3 torques. And this torque is also going to be a row vector as a result. So we're multiplying on the left here. You can see, you can count the dimensions. So, what's going to happen? What we actually did is, and I made the dependence of this Jacobian on the joint coordinates explicit here in this formula. I didn't do that here, but these co-axes all depend on the joint coordinates. So this is the very well-known Jacobian that transforms joint velocities into actually the motion of the frame of the body. But if you multiply this on the left with a row vector, that's the same as the Jacobian transpose, then it also establishes a relationship between the wrench and the torques. Okay, and this is basically exactly the same recipe, just packaged a little bit differently to make the connection with robotics easy. All right, so what can we do? Well, that means we can create with a little bit of GTSAM code, a little bit of Python code, I should say. There is a very little GTSAM here. We created a function, forward kinematics, that calculates these frames, which you'll need. That just takes 2 joint angles and some dimensions for the legs, 3 joint angles, and where the third joint is in the body frame. So we get 3 joint frames for that, all expressed, by the way, in the body. Okay, so this is joint frame 1 in the body, joint frame 2 in the body, joint frame 3 in the body. Now we calculate J transpose, so we're going to do, we're not going to use this function z, which was using that dictionary, so we'll just do the adjoint map. As is customary, you take the third column of the adjoint map, and that's going to be the 3 joint axes, and we just collect them as rows in the Jacobian, and that's going to be J transpose. And then finally, we do a little bit of GTSAM. Here we add a factor that says what the linear relationship is between the wrench and the torque vector. Okay, it's in this case it's a full rank relationship, so it's a 3 by 3 Jacobian. But if we have less torques, okay, then it could be less than full rank because we have fewer torques than the wrench coordinates, or we can have an over determined system. If we have more than 1 torque, we'll have to resolve that over determinacy somehow. But you know, so the Jacobian J doesn't have to be squared, is all I'm saying here, and it is not if you have more links in your leg. Okay, so now that we have a leg factor, all right, and probably I should learn from my mistake above and say and evaluate this cell. I'm just going to give an example of what Jacobian transpose does here. So here, what I did is I took lengths L1 and L2. I put the joint angles to 0, which is basically a straight leg. I added a location which I eyeballed of the joint 3 in the body, so that's like minus half, 50 centimeters this way, 20 centimeters this way. Now this is a fairly large dog, but let's go with the numbers I put in. You can put in more realistic numbers. So minus 5 and minus 0.2, and I multiplied it with a gravity wrench to see what that gravity wrench would induce in the joints in terms of torques. And what you can see, there's a gravity wrench of 10 Newton would create 5 Newton meters, all in the clockwise direction, which seems reasonable, right? And of course, the joints will have to cancel that if the robot wants to remain standing up. So let's, with this leg factor, which is now talks about all 3 torques at the same time, our factor graph becomes much simpler, right? So we have only 2 unknowns, which is the wrench at the hip on the left, on the hind leg, a wrench at the hip on the front leg. Here is the body, which is cancelling the gravity of the robot. Now the definition of the torques in terms of the wrench is given by this Jacobian transpose relationship. So that's green. So I use green throughout this notebook to indicate what the definition is of a torque, or how it relates in general to the wrench. And then I'm going to say, let's assume that we don't have ankle actuation, so that the torque at 1 and 4 is 0. And then we want to minimize the other 2 torques at the knee and the hip. Okay? So this is the entire factor graph for that robot. So tiny factor graph, tiny piece of code, right? So here are the minimization factors. So let me try and see whether I can get the factor graph and the code at least a little bit on the same page. So here is these 2 torque factors. That's the first 2. Then we have the Jacobian transpose factors, which we just called leg factor, and add that. This is now going to be a 3-dimensional relationship. Okay, and then finally we'll add the body equation, and that's going to be simple. You don't really need to see the factor graph for that. So this is the body equation, and then we also say, which is, it's a little bit redundant with torque minimization here, but we can still say, hey, make the torques 0. Then these 2 factors are just going to disregard that component of the torque because this one forces them to 0 anyway. So this is going to become a least squares on the remaining 2 dimensions. Let's I added a little piece of code to and I have to evaluate this. Let's evaluate it. I think that worked. This is just I'm not going to show you the result yet, because what I wanted to do first is show that I got the forward kinematics right. So I used some functionality in GTSAM which is called plot trajectory. This is not so important, but I just added all the poses into values, and then plot trajectory can just plot it. It does it in 3D, so I have to sort of make the axes be orthonormal and looking from the z direction. So this is with the joint angles that I specified above, the forward kinematics. Note that the body frame here is 0, 0, so this is all relative with respect to the body frame. And this is then the supposed ground plane, and apparently it's standing on a little plank with these kinematics with its hind leg. And the front leg is a little bit down. That's because this joint angle is a bit larger than this one. And I created those joint angles to give interesting results. And I already showed the outcome actually of solving the factor graph. This is in fact the force component of the wrench that shows that there is this large gravity, and this one balances it. And something else interesting that happens is that you can see that these reaction forces, which are really just the ground reaction forces but transmitted to the hips, you can see that they're oriented in such a way, okay? And this is a real phenomenon in animals and people. Okay, there is a recent Caltech review paper by Dickinson and co-authors where this is explained in detail. I think it's a Nature review paper. It's very interesting. Ground reaction forces are oriented by applying the necessary torques to minimize the torque. So there's a minimizing the torque. Okay, if you continue this line of action, it's going to almost intersect the joint axes, which will lead to the smallest possible moments. Okay, and so you see that when walking, that these ground reaction forces actually shift and actually change as a person walks. For example, the ground reaction forces change the direction to continually line up with the joints, which is very interesting that we get this as a result here, just by saying minimize the torque, please. And let's print the result as the final outcome here. And so you can see that I'm not actually plotting the torques in this figure, but I show them here numerically. We have the two unknown wrenches, and the torques are now 3 vectors. As asked, we put the ankle torques to 0, and then the knee torque and the hip torque are as shown here. So we with the joint the angles that we gave, this is the numerical result. Okay. And as before, by the way, we don't have to put the ankle torque to 0. We can maybe we can have a passively actuated ankle by putting a spring there, maybe a torsional spring, and then the weight that will be given to GTSM, to this minimization problem, will actually be the torsional spring constant. So it can deal with unactuated joints that nevertheless can be sort of taken into account. Then the other weights will be sort of given as ratios of that spring constant. So you have to be sure, take care of your units and make sure they all agree. But that's one way to include compliant mechanisms, right? Many studies in animal studies and human studies actually have compliance, that is models. Many simplified models use compliance. But take a look at this factor graph again, okay? This factor graph has the entire statics of this articulated robot into this very simple structure. And with that, we can already model compliance, joint transpose relationships, weighting of the torques. And we don't do this on a per leg basis. The entire mechanism is reasoned about by simply having 1, 2, 3, 4, 5, 6, 7 factors in 4 unknowns. This is, of course, not unknown in robotics. Many robotics papers are about whole body control, where they solve a system like this. The torque here then in the ankle is typically also 0, but we actually will then also model constraints on what friction can deliver in the feet. So then this becomes a quadratic minimization problem with equality constraints. These are all equality constraints. This is the minimization, but then we'll also introduce linear inequalities, or in fact nonlinear inequalities, to to model friction cones and the like. All right, so that concludes my my lecture series here. But let me add one note about indeterminacy, okay? And that is, sometimes you simply cannot solve for the unknown static forces in the mechanism. And this is very well known in mechanics, okay? In fact, the humble table with 4 legs, if you put it on frictionless ball joints, you can move the table wherever you want and you can rotate it and it will not be able to resist those. But the other 3 components of the body wrench, or the table wrench I should say, are the force, the vertical force, and then the 2 other torque components. So that gives 3 degrees of freedom. That's going to be 3 unknown equations. Sorry, three equations in the unknowns. What are the unknowns? The unknowns are the 4 ground reaction forces in each of the 4 legs. Well, it turns out you have 4 unknowns and only 3 equations, so guess what? It's indeterminate. So if you actually give this to GTSAM will throw the dreaded indeterminate linear system exception, say, you just didn't give me enough information to solve this system. And so we have to take care, if you use GTSAM for dynamics and statics as we want to do, that we actually make sure that we know when we have an indeterminate mechanism at our hands. That cannot be resolved with minimizing torque or something. In this case, it's the statics, the passive statics are just indeterminate. And that can happen in a 4-legged, like a dog is just like a table, right? So there we have this indeterminacy. So you have to be careful with that. You might think that, so in the planar case, I actually show a half-spider example. If we introduce 4 wrenches, which will 12 unknowns, 8 forces, and then 4 torques at the joints. And it turns out that we have only 11 constraints in this half-spider example. So the half-spider is immediately indeterminate. And there is nothing we can do with torques to help that. This is the table thing. Maybe you're thinking, oh, why don't I add like sort of more intermediate links in the legs? But every link you add adds an additional unknown of 3 degrees of freedom, and 1 additional link equation, which is also 3 degrees of freedom. So adding links is actually a no-op. You can have like 17 links there, and it won't make a difference. So this half-spider is going to be indeterminate no matter what. So I thought that was interesting, because it could come to bite us. Okay, look, so that's it. Let me just go back to the beginning of this lecture and show this beautiful Star Wars themed dogs can be modeled with this beautiful little factor graph. It's a planar example. It's not much more complicated in 3D, but it's sort of easier to understand in 2D. Here is the dog, and I'll conclude there and hope that you'll have some fun playing with this notebook if you're so inclined. All right.